We got this half rack with the 1.23 petabytes. 1.23 petabytes of flash storage right here in this roughly fridge-sized rack. But wait, it's actually just that. Just the 1-2U server, and we're only using the little tiny thing on the side. There's only 5 of those 1.23 petabytes. That's madness. I feel like Doc Brown in the 1950s when he's like 1.21 gigawatts. I'm sure that you can pick up uranium at any corner drugstore. But here in it's madness, absolute madness. .23 petabytes of storage, I mean, that seems kind of pedestrian. Everybody's got a petabyte of flash storage at this point, except me.
Yeah, well, I'm Adil Rahman. I'm a senior engineer with Kioxia, and for us, this is a walk in the park. We can get 1.23 petabytes of storage off of 5 of these 3.L drives.
Just 5 of those is giving us 1.23 petabytes? This comes as a complete surprise. That must mean that's 256 terabytes in one device.
That's exactly right. And it uses the EDSFF form factor, so for the thermals, it is great, and it is a PCIe 5.0 drive, so its performance is great. Everything about it is just really, really good for AI workloads.
But this 256 terabytes in it, you have to change the NVMe specifications. Like, you would have to, I mean, it would need 256 gigabytes of DRAM, DDR5, and you don't have the power budget for that. How do you do the engineering necessary to make that happen?
Well, we have our magic sauce from our manufacturing processes in Japan, and Kioxia is at the leading front of storage technology. So we have even more drives, especially for these AI workloads that are specialized for GPU-initiated access. So traditionally, you would have to go through your CPUs, and there's a lot of overhead that happens when playing middleman and having that communication back and forth between your storage and your GPU. Well, now we decided, hey, we can do direct copies from GPU memory into NVMe, and we created a localized drive that uses an E1.S form factor called GP, and that accesses at 512 bytes, and GPUs love that. They love having small, little fine-grained access in that sense. So really, really cool stuff.
So with this platform, you're offloading potentially KV cache. It's like a third-tier device, but it is directly GPU accessible, so that lowers latency and all of that. But it's not just KV cache. You can also do inferencing. You can also do a lot of the tasks that typically overrun GPU VRAM. And if you got enough of those on a large enough fabric, it's fast enough, you can do things that you can't otherwise do because you literally lack the VRAM.
Exactly. And, one instance of not even outside of training and inference is like graph neural networks, for example. This will love that kind of application because the GPUs get to access everything that you need. So you may have an application where you're trying to do like a fraud detection network, and you need to have a really, really large graph that goes through a ton of context and a ton of time. And the more capacity that you have for these types of applications, the further back you can go and go, I don't know, something's off about this guy. I'm going to block this thing and give the actual user notification that someone tried to use your card. There's a lot of different applications that GPUs really are successful in when using a drive like this that really caters to the GPU. And on top of that, we go to LC9 with QLC with NVIDIA Dynamo, where you have smart routing, able to place all these different blocks across different memory tiers. Your G1 at HBM, your G2 at
LPDDR5.
Yeah, with your system exactly, DDR5, and then it goes from local NVMe, and then now we can do RDMA and literally go to a disaggregated storage box full of QLC drives of 245 terabytes, and all of a sudden I can service 1,000 users, hundreds of thousands of users, and all their different context windows. This is all enabled through NVIDIA's Bluefield DPU NIC, their 4th generation, which is an 800 gigabit per second NIC. It goes through Spectrum X switching, and essentially to get full PCIe Gen 6 performance, which is coming in the future, of course, you can pretty much saturate a Bluefield NIC in terms of throughput with 4 of those drives.
And this is part of NVIDIA's new storage architecture they announced at the keynote?
Yes, exactly. So with NVIDIA's reference architecture, typically lists E1.S as the primary form factor for their reference architecture. They're aiming for 4 to 8 drives on their general compute nodes, and then their storage nodes, you can scale that separately from your compute so that you can have dedicated pods that are dedicated for pre-fill steps and decode steps and whatever in the inference layer.
And that makes sense with the Grok because you can also do some of the offload with Grok, and then Grok needs to be fed.
Exactly, yeah. So it's really, really cool stuff where, Kioxia is really going out of our way to make specialized products for AI workloads that will really fit for the different stages and also the different types of data that you're trying to store and how they're going to be accessed and really thinking about data locality in a new way.
Yeah, cool. All right, is there anything else you want to show us about the demo or what's going on? Like, what's happening?
Yeah, so on that note for our GP drive that has that 512 byte access, we're able to get 10.5 million IOPS off of a single GP1 drive. Now, granted, that's with a 512 byte block size, but that's still nothing to scoff on,
Yeah, it's hard to do 10 million IOPS with a 512 byte block size on NAND.
Yeah, on NAND flash, by the way. So it's very good, and by 2027, we actually have the roadmap to get that up to 100 million IOPS.
Wow, 100 million IOPS.
Yes.
That is absurd.
Yeah.
How are you doing that without RAM?
So it is powered by SLC, right, this GP product, and we're really aiming that low latency because you really don't want that time to first token to get impacted by going to a slower medium. And by keeping it in the microsecond range, your NVLink and all that's still going to be in the nanosecond range, and that's great. But when you're doing decode steps, especially the sequential manner of how decode is, you really don't want to be slowed down by your slowest drive, right? And if your slowest drive is still 10 to 15 microseconds with an RDMA access from a Bluefield NIC, well, that's pretty damn good, right?
Yeah, that's really great. Well, and also thinking about the parallelization, it's like you've got a box that's got all this VRAM, and you've got 10,000 users' data loaded, and the sessions are like medium warm. Like you have some users that they're constantly generating inferencing, and you have some users that generated some inference, and then like they've got to look at the output or they've got to do something, and it just keeps running. And then also like agentic, like an agentic AI, it's like it's not going to really matter all that much the speed as long as it gets done in a reasonable amount of time.
Exactly. The difference between a second and 2 seconds is negligible as long as you're reading on the screen the first token and then you're starting to analyze as a human being. It's kind of like boot times with SATA and NVMe sometimes, or SATA and SAS. It's hard to tell the difference between a second boot time and 1.5 seconds of boot time.
Well, if I've got an agentic job running and it's the difference between this completed in an hour and this completed in 8 hours, I might not care depending on what the thing is that I'm doing. It's like, I want you to optimize this use case. I'm going to go to sleep now.
Exactly.
I'm not going to. It's like you get done in an hour, 8 hours. It doesn't matter to me.
Yeah. I'm going to get 9 hours of sleep anyway, so an hour later, it'll be all done.
Yeah.
Exactly.
Yeah.
So a lot of our drives are really getting catered towards what exactly are we trying to run the AI on. And, traditional TLC media did an okay job at that, but what we can always do better, right? And that's what we're always striving to be as technology leaders and showing that, the storage is capable of doing a lot more. And as we have more problem statements that we need to solve, well, storage is kind of stepping up and saying, hey, you need memory, you need a place to put that storage. Well, we have pretty decently fast storage tiers here. Yeah. We can fill in a G3.5, a G3 tier, and even at that G4 tier of like archivals, object storage, and all that, well, you can equally use QLC for that as well. As long as you have a read many, write once type of application, you don't have to worry too much about the endurance in terms of QLC.
So this drive is operating in SLC mode, 32 terabytes? Is that how that works?
Well, for the GP product, because of that E1.S form factor, it's really hard to stuff 30 terabytes of NAND inside of that form factor. So,
E1, that's E3.
So this one's E3. So this is the LC9 product for QLC. GP1 is the SLC product for that local NVMe tier. And for the local NVMe tier, you're probably going to expect more in the realms of an 8 terabyte or a 16 terabyte max capacity per drive.
8 to 16 terabytes in an E1 form factor of SLC. Single level cells. That is bananas.
Right. And with the SLC, traditionally you would see like 800 gigabytes or maybe 3.2 terabytes at max, but we're getting so dense in terms of the layer count for the NAND that we're able to really expand upon the
It's just a brick at this point.
yeah, it is literally just a brick. So, and they're so light and so small, and now that we're kind of coming together as an industry in terms of a new form factor, a new connector that's universal across that EDSFF family, we're really starting to get somewhere in terms of unification. So
Cool. Anything else we haven't asked for?
Well, I mean, last off, talking about inferencing and whatnot, you have that question of, okay, sure, I got my time to first token down really low, but the response of that answer it doesn't make any sense. It's completely wrong. So what do you do in that instance? Well, you have RAG, right? You have retrieval augmented generation. You feed a vector database, your proprietary
Extend the context.
data. Yeah, exactly. And then there's another problem. It's like, well, how many vectors can I store? How much media can I store? Traditionally, you had HNSW, which was completely in memory, but again, same scaling problems that you were having before. Now, with Kioxia's ISIC technology, we're able to actually offload all of the vectors, not only the quantized vectors.
Dynamo.
Yeah. Well, Dynamo is for the inferencing side, then ISIC is for the RAG side, even separate to that. So you can run RAG separate to Dynamo if you really wanted to. But with RAG, I can now say, hey, store all of the vectors and everything for the data that I'm feeding into you, use it as a separate source of truth so that you feed that into the context window of the model.
But selectively.
Selectively, and it grounds your model so that you don't hallucinate nearly as much. And then now your recall and all those things go up where you're getting to the 99% recall or 90% recall for, top 10 similarity search. And you get really good performance. Isaac's able to go up to 4.8 billion vectors, and you can still get a queries per second of about 200. Your latency goes down to about 50 microseconds. So compared to some traditional solutions where you're just doing a blind sharding, you can get up to a 4x performance improvement, which is really, really huge at that massive data set size.
Yeah, that is a lot of impressive machinery being added to, combat the hallucination problem. But having the actual document or the actual reference material in the thing that it's using when it's doing the inferencing seems like that's a great way to combat that.
Absolutely.
But that demands more storage.
Exactly. So you need more storage. But the good news is that the ISIC technology is open source. You can go to GitHub, you can go to the Kioxia GitHub page, download it, take a look at it, and use it. And you can use it on your beautiful Kioxia storage that is meant, has its use cases depending on where in the stack you are for your AI workloads.
Cool. Yeah, that's awesome.